Okay, welcome back to the third part of this topic, the third and final part of this topic. Um, Before moving forward, I want to come back and just re-look at that circular motion one. So we had something, we had talked about something like this, where if the velocity is perpendicular to the B field, you will always get this inward pointing force. So you'll have centripetal motion. Um, and then we talked about, let's see, hold on. We talked here about an electron gun. So an electron gun heats up, like it's like a cathode diode type thing. It heats up and creates a potential difference, and it shoots some electrons in a straight line. However, if that is placed inside a magnetic field, instead of a straight line, it'll loop around. So I didn't have this video in here, and I want to show it to you now. This is actually in our lab classroom. This is a lab that we would have otherwise done, other than being in a pandemic and all. So what you're seeing here before I press play is the electron gun. It has heated up, so there's a potential difference. So this is attached to a potential difference. So imagine that there's a plate over here and a plate over here. One side is positive, one side is negative. And then you start to strip electrons off of this plate. And so what happens is, due to the potential difference, they stream over like this. And that's what you're seeing there. That little greenish glow, that's a stream of electrons. They're placed inside a tube so that we can see them as they ionize some gas. I think it has maybe some neon gas in there, some other type of gas, so that as they move through it, they ionize it and we can see it. So what you're seeing right now is just an electron gun shooting the electrons straight in just in a straight line, as Newton's laws tell us. Now watch what happens when the when the magnetic field is turned on. So all around here is a ring that will cause a magnetic field. So once the magnetic field gets turned on, watch what happens. Boom. Oh, shoot, sorry. Let me try that again. You saw how it suddenly curved. That's exactly when the magnetic field gets turned on. Right there. Magnetic field gets turned on, and then we can turn it back off again. Yeah. So that's pretty cool. I've always enjoyed that. So I just kind of wanted to show you that video because I didn't have it in last time. So, all right. So we had looked at the current on a straight wire. And remember that we use a very similar right-hand rule to the one like a moving charge, right? Because our current is just a moving charge. So our fingers go with the current, which in let's see, in this picture here is moving upwards. I don't know which way my palm is going to face yet, but I see that the B field has X's, so I'm looking at the back of the arrow. So my B field has to point in towards the board, and that gives a force to the left. And so the wire physically arcs to the left. And then in the picture over here, now my fingers go with the current. Now it's downward. Yeah, it's downward. And the B field is in, and now it's pointing to my right. It's hard to see way up here. It's easier to do down by your hips, right? So if you're sitting at home, it's easier to do down by your hips. Don't do it with your left hand. Can't do it with your left hand. But then you see that it gets a force to the right that physically curves this over to the right. But notice how this says for a straight wire, okay? What's gonna happen when we change that straight wire for a curved wire? Well, let's see. Hold on, my computer's being weird. Okay, let's see what happens. Okay, so now if we have a wire that is not straight, any arbitrarily shaped wire, well, think about what happens. As the current flows through this wire, the direction of the current physically changes, right? Because the shape of the wire physically changes. So the angles between the current and the B field are going to change at every point. right? Those angles are not the same. Those angles are changing as the direction of the current changes. So instead of writing it as, so as we had it, IL cross B, what we're going to do instead is we're going to take this total length and break it up into little itty bitty pieces of length. Right here, the total length doesn't change direction, so I can just look at the whole thing. But if I have chunks that are changing, now instead of looking at the total length, I'm going to look at little itty bitty pieces of it. So this DS, think of it as a DL, little tiny pieces of length. And at every little infinitesimal length, what is its orientation with the B field? So if I want to find the total, then I'm going to integrate. So let's see how that would look. Let's do a semicircular conductor. Now, I can break this up into two pieces because I have a straight wire here. A straight wire with the current pointing to the right and the B field kind of pointing, if I'm looking at my iPad, it's pointing straight in the direction that I'm looking. Okay, so let's see if you can see me. Hi. So let's figure this out. Current, fingers. So fingers have to point to my right. And then the B field, as I'm looking through my iPad or you're looking at your sheet of paper, is pointing straight in the direction that you're looking. So my palm has to point in the direction that I'm looking, and that gives a force that comes up out of the page, right? So this piece of wire, this straight piece of wire, so fingers to the right, B field straight forward, thumb up. So this piece of wire feels an outward force, just the straight bit of the wire. But the curved bit, that's going to change, right? Because the current is changing orientations with the B field at every point. In fact, here there's a 90-degree, right? But like here, there's a 0-degree. So it's changing orientation. But we can get a directionality for it before we do the integral. We can get a directionality for it. My current is kind of flowing around in this direction, right? So I can have my fingers over kind of right over here, and then they kind of arc this way, and then they're going to come down this way. But at every point along the way that I'm doing that, the B field is pointing that way. So I've got to turn my palm all the way around. And that's going to give a downward force. And I can do that for kind of every little step along the way. Right now I can look at maybe over here. Okay, so over there, my fingers with the current is pointing this way, but the palm has to point that way with the B field, so down. So this whole curved portion gets that type of a force into the board, down. And this one gets out of the board, and this one goes into the board. So now we're going to break this up. We're going to look at the straight wire. We can do that piece. And then we're going to look at the curved wire. For the straight wire, we don't need to do the integral because the angle doesn't change. The current is always to the right. The B field is always facing forward. And so the force will always be straight up. So let's pull this up on a whiteboard. Okay. So for the straight portion, right, for the straight portion of wire, we have current, that's going to be your fingers. And then the B field is pointing that direction. That's going to be your palm. And so the thumb is going to come like out of the board. And that's going to be the force, and that's your thumb. So the force is out, or we could call that the positive K hat direction. But what is the magnitude of it? Well, for the straight wires, right, our equation says F of B is equal to I L cross B. I L cross B. Remember that L is the length of the wire, but the directionality flows with the current. So really, if I want to look at the magnitude, then I'm going to look at I L B sine theta, where theta is between the current and the B field. Well, the angle between the current and the B field is 90 degrees. And sine of 90 is equal to 1. So for the straight portion of the wire, we get a current of I times L times B, and we know that it is in the positive K hat or out of the board. Okay? And we're going to hold on to that. That's what's happening with the straight portion of the wire. Okay, now let's look at the curved portion of the wire. Oh, sorry, I want to do one more thing because actually I'm trying to get this in terms of R, the radius given. Okay, so I'm going to do one more thing. I'm going to draw another picture here just to show that piece. That would be a perfectly fine answer if I was given R, sorry, the length, but I'm not given the length. Instead, what I'm given is on an XY axis that this is R, so that the length is actually 2R. Okay, so that when I come over here to do my arc, I also want to write that in terms of R. So for the straight portion, instead of writing it as L, I want to write it as 2R. So this gives me I times 2R times B, and again, in that positive K hat direction. Now let's look at the curved portion. Okay. So now let's just focus on this curved portion. And again, here's our R, right? The same R. B field points straight up at every direction, at every point. That's not changing. What is changing is the direction of the current, right? So the current is flowing along this way, but you see that it's changing orientations at every point. So we're going to take the infinitesimal portion of it and watch it as it moves around. So for the curved portion, the infinitesimal force at every little tiny bit ds, every little tiny bit ds, okay, is going to be given by the current times how every little bit of ds, or portion of that length, is oriented with the B field. Okay, every little bit. So if I want to find the total force, I'm going to integrate both sides, and the current is constant, so it stays in there. Let's look at this ds cross B. Okay, the magnitude ds cross B says take the magnitude ds and the magnitude B and the sine of the angle between them. Okay, now that sine of the angle is going to change. And I know we already determined that it's in the negative K hat, right? We did our right hand rule and our thumb pointed down towards the table into the board. Okay, so what are we going to do with this ds? Well, just like we've been doing, we're going to turn that ds into an r d theta, right? Just an arc length. So remember, a full circumference gives me an r times the full 2 pi. So a little bit of the circle gives me an r times a little bit of the thetas, and then I can do infinitesimal ds with infinitesimal d theta. Okay, so let's replace that ds with r d theta. So that our df of the curved part is I ds crossed into b, which is I times ds times b times the sine of theta, which is I times r d theta times b times the sine of theta. And then I want to integrate both sides. So the force, the current's going to come out, R is going to come out, B is going to come out, and we're going to get a sine theta d theta. And our limits of integration are from 0 to pi, and we have to be in radians, right? Because C is only r times 2 pi r when we're in radians, and therefore ds is only r d theta when we're in radians. So must be in radians. So we get the integral of sine d theta from 0 to pi. 0 to pi because if we look at our curved wire, we're going from 0 to pi. Okay. All right, so we integrate from 0 to pi, and we get, so we get, I need my pencil. So we get I times R times B times the negative cos of theta from 0 to pi. Okay. So we get cos of pi is -1. We get -1, -1. Okay, so that gives me a -2. So we get that the force is -2IRB. So let's put that together. That's for the curved portion. And that negative, again, because we know it's in that negative k hat. So let's look at the net force then. We have everything there. So for the straight, what did we get? We got 2IRB in that positive k hat direction. And for the curve, we got 2IRB in the negative k hat direction. So I have one positive, one negative, and the net force is 0, which is kind of cool. All right, so the net force is equal to 0. That leads us, so now what we're doing is we're looking at how wires have forces on them. Let me come back here. Wires have forces on them that can move the wires. And when we create these loops of wires, because one side has a force that pushes it out of the board and one side has a force that pushes it into the board, the net force is 0. But wait, can't I make this spin? If this bottom portion is being pulled up towards me, right? If this bottom portion is being pulled up towards me, and this portion here is being pulled down, that's supposed to say down. I don't know why I can't write on these things. Down, okay? I can imagine that this whole thing is rotating such that the top part gets pushed into the board and the bottom part comes out of the board, and I'm creating rotation. So that leads us right into torque. I can have forces pushing on these loops in such a way that one side is pushed in, one side is pushed out, and it rotates. Wait, this is actually really cool. What we're saying is I can have a loop of wire. I can run current through that loop. But then, as soon as I place it in a magnetic field, this loop is going to start to rotate, spin in one way or another. And then, hold on, I can use that rotation for mechanical energy to do something, do some work. I've just created a motor. I've created a motor by running current through a loop of wire and then placing it in a magnetic field. And this is what motors are. Okay, a motor uses current to do mechanical work. Now I can use that rotation to turn a car wheel or something like that. Okay, like an electric motor in a Tesla. It's going to run current. That current's going to make something turn. An engine is the opposite of that, and we'll talk about that later. An engine is when you use mechanical. Well, an engine uses combustion, a motor uses electricity, and then a generator is when you run it backwards. We'll get all of that detail worked out, right? So motors are electrical, engines are combustion. So Tesla is a motor. General Motors is actually General Engines because they use combustion. All right, so let's see how all of this rotation stuff works, right? How is this going to happen? All right, so let's take a wire, just like this, a loop of wire, run some current through it. All right, cool. No big deal. But let's place it in a magnetic field. All right, so let's see. Are these all straight segments of wire? Yeah, so I don't have to do the integral and worry about the angles and all of that. Let's look at pieces 1, 2, 3, and 4 independently. Okay, so piece 1 has the current pointing to the right and the B field the current pointing to the left and the B field pointing to the right. Now, you're trying to do the right hand rule and you're going, okay, so fingers go to the right, but palm goes to the left. I can't do that. Oh, right. Cross products look for perpendicular components. And what's the cross product of parallel or anti-parallel? 0. There's no force here. And you could say the same thing about the bottom. The current to the right and the palm to the right, I can't do that. I can't do that, right? So parallel and anti-parallel components have 0 cross products. So they have 0 force. So that top portion and that bottom portion do not feel a force. Okay, so let's look at sides 2 and 4. Let's go with side 4 first. So side 4 has an upward current. So place your fingers. I'm looking down at my iPad, so my fingers are pointing straight that way, straight the way I'm looking. The magnetic field is pointing to my right, so I have to turn my palm to the right, and the finger points down. My thumb points down. So this side 4 has a downward force. Okay, and now let's do side 2. So now the fingers point towards me. B field points to my right, so I have to turn my palm that way. And the thumb, the force, points straight up. So side 2 has an upward force. So what's going to happen? Side 4 is going to go down into the page as side 2 comes out of the page. This should have a little dot in it. Okay, so it's going to start to rotate, like the right side coming out of the page and the bottom side going into the page. So imagine something like this, right? Grab your notebook, pull your right side up as you pull the left side down, and it starts to rotate. So you can get this to rotate simply by running current through a magnetic field, which is pretty cool. Okay, the net force is still going to be 0. The net force is still going to be 0, but if I pinch it somewhere, if I clamp it, let's say I clamp it right at this midpoint, right? Just like I was doing with my paper, I'm clamping, I'm physically holding it down at the midpoint so that that's the rotation of axes. And we're going to get rotation like this, right side up, left side down. But then the force is still 0. All right, so let's go a little bit further. So we've determined that top and bottom are parallel and anti-parallel. They don't contribute, but right and left, they're going into the board and out of the board. And if I were to clamp it somewhere, it would start to spin. Okay, I'm gonna disappear for a little bit. So that's exactly what we're gonna do. We're gonna make this loop pivot and rotate around this halfway point, okay? So in essence, what we're doing is we're creating a torque. We're applying a force at a distance, right? Just like our physics 195, except this force now is the magnetic force. So what we're doing in this picture is we're looking at a side view of our loop. So now imagine that instead of looking down on the sheet of paper, you're looking at it like sideways, like this, okay? So that you're seeing one force go up and one force go down, okay? All right. So you have a force acting at a distance, okay? And because we're looking at side 2, like the top wire, or sorry, which one is side 2? Let me get that back. We're looking at this wire here, okay? So wire 2 is coming out, the current is coming out towards us, and wire 4, the current is coming in towards us, right? So this force was now down and this force is now up. And notice how the current is drawn as the tip of the arrow coming out towards us. And this current is the back side of the arrow, the feathers going in towards the board. And we're going to rotate it, pivot it around that origin. So the force at a distance creates a torque. And this force at this distance creates a torque. Okay. Now, if we want to look at the maximum torque is when the sine of theta is sine of 90, which equals 1. So then what we're going to have for this is the torque from force 1 and the torque from force 2, which are called 2 and 4. I'm sorry. Okay. So on one side, the distance to the force is b over 2, and the force itself is force 2, right? So the distance to the force, remember that this whole thing was b, so this side is b over 2, and this side is b over 2. So the distance is b over 2. And the force, well, one of them is F2 and one of them is F4. Okay, but what is that force? What is that force? Well, that force is I times A times B. So let's see where that force of IAB comes from. Okay, so we have to go back to our other, whoops, wrong way. Here we go. How did we get, so we want to figure out what the force is on each of these. Okay, let me get my pen up. What my force is on each of these lengths of wire, each of these segments, right? Those are the ones that I'm seeing here as F2 and F4. Okay, so from here, I want to find that force that is going to push that side, right, kind of out of the board. So this would be an out force, and I want to find the force that pushes that in to the board. So let's look at that separately, and then we'll come back to the torque. So if we look at side 2, has current going down this way, a B field going to the right, and we know the force is going to be out of the board, but we also know that the angle between the current and the B field is 90, right? So when we do the magnitude of the force is equal to I times L times B times sine of theta. Remember that theta is between the current and the B field, so that's going to be 90 degrees. And sine of 90 is 1. So the magnitude of this force is I times L times B. But L here is given, if we look at our picture, it's actually given as lowercase a. So that is I times A times B. L is a generic placeholder. In this particular picture, it's given as lowercase a, and we know that it is out of the board. And then we can do the same or similar thing to the other side, side 4. And side 4 has a current that flows up this way. The B field still points to the right. So we decided that the force is going to be in. And we still have a theta of 90 degrees. So we get the same idea. F of B is I times L times B times the sine of 90. And so this gives me ILB, but again, that L was given in this drawing as A. And in this case, it's in. So what I get is I get a force of each of those of IAB. So going back to the torque, going back to our torque, here we go. So the force is that IAB. The distance is this distance right here. Come on, pen. The distance is this distance right here, which is B over 2. So I just replaced the B over 2 for my distance and the IAB for my force, right? And I get that on both sides, And for both of those, I get a clockwise rotation. This creates a clockwise rotation and this creates a clockwise rotation. They're both pushing in the same direction. So I'm going to add them and I get a torque of I times AB times B. And what are A's and B's? Well, that was just particular to this exact problem where A was this length of wire and B was that length of wire. Okay. So what ends up happening, like we said then, is we get a rotation, right? We're pinching about the middle point. We're pivoting here. And so we're going to get a rotation that ends up looking like this. One side feeling an upward force, one side feeling a downward force, and we create a torque. And for torque, we're looking, notice how here I'm looking at the maximum, right? And the maximum is when these forces are perfectly perpendicular to that lever arm, to the distance between the pivot and the force. Okay. So that's the torque. Now, we also see something here. I see this AB. Well, AB is actually just the area of the loop. Remember, we had a loop, and this was A, and this was B. So the area of the loop is AB. So I can replace this with the maximum torque is the current times the B field times the area of the loop. And this is exactly the equation that we want. Now notice how this is maximum. Maximum means that the forces are lined up to give us that 90 degree direction, right? That gives us the maximum. There'll be times where we won't have the maximum. Okay, so what happens when we don't have a maximum? Well, the maximum is when that cross product equals 1. So the maximum is I, A, B sine of 90. The maximum is just I, A, B. But at any other orientations, I have that cross product. So to find the torque on a current carrying loop, I need to know the current. I need to know the B field. I need to know the area of the loop. And I need to know something about directions because these are all vectors. And now this is really funny to me. It's always been funny to me that they put the vector on the area, which is kind of silly because area generally doesn't have a direction. Okay. But it's really following the direction of the current. Okay. So what is this a vector? Well, the magnitude is the area of the loop. That makes sense to us. What about the direction? The direction here, in order to make this work, is a direction perpendicular to the plane of the loop. Normal, the normal to the plane of the loop. Okay. All right, so here's our loop. Here's our loop. It's flat on your table. So which way is the direction of this area vector pointing? Well, it's either going to point up, normal to the loop, or it's going to point down, normal to the loop. It's not going to point along the loop. It's going to point either up or down. And how we're going to determine that is we're going to follow the current around. If the current flows around clockwise, curl your fingers around clockwise, and that area vector will point up. If the current flows counterclockwise, follow your fingers around counterclockwise, and that area vector will point down. I know it's kind of silly to give like the vector to the area and not the current, but it's just kind of the way it works. So think about having your fingers curl with the current, and that gives you the direction that this area vector points. Curl with the current the other way, clockwise, points down. Okay, so it's normal to the loop. All right. So what we want to do, so we have that the torque is IA cross B. Well, this IA has a different name as well. We call it something. This IA, we're going to call it the magnetic dipole moment. The magnetic dipole moment. What is moment? It's like moment of inertia. Remember moment of inertia? It is the tendency of an object to resist any changes in its motion. Rotational inertia is the inertia that a shape has to keep rolling, keep spinning, keep doing what it's doing. It's going to resist. Inertial mass is mass, and that's how well an object resists change. So I have, small mass. A linebacker in football has very large mass. So a linebacker in football has a large inertia, larger ability to resist change. Me, I have smaller mass. I have smaller moment of inertia, smaller ability to resist change. So if you go push me, don't do that. But if you go push me, it'll be pretty easy to move me. I can't resist that change. If you go push a linebacker, probably not going to get him to move at all. There's a lot of resistance to change. So now we're taking loops of current, right? We run current through this loop, nothing happens. But if we place it in a B field, now, woo, this whole thing starts to spin. But of course, what is it doing? Well, it's just laying there. And then it was going to start spinning. There's going to be some inertia associated with it, right? And just like our rolling objects have a moment of inertia, well, this is going to have an inertial moment to it, except this one is based on magnetism. So the name for it is magnetic dipole moment. What is it? It's a tendency for this loop to align with the B field. It wants to align with the B field, but is doing so in such a way that one side is being pushed down because it wants to align with the B field, and the other side wants to push up because it wants to align with the B field, and it just starts spinning and rotating and spinning and rotating. Okay? So let's look a little bit more at that. We're not really introducing anything new. We're just calling that term the moment of inertia, mu. Sorry, the magnetic dipole moment. Okay, it's the object's tendency to align with the B field. That's just what it wants to do. It's going to have units of, well, let's see, area has units of meters squared and current has units of amps. Which direction is it? Well, it's perpendicular to the plane of the loop because that's how it wants to align with the current. So then we can replace that IA and write our torque as mu crossed into B. Let's work some examples here and kind of figure out how this looks. Okay, so again, how do you find the direction of the magnetic moment? It's going to be perpendicular to the loop, so either straight up or straight down, and you're going to find it by curling your fingers around with the current. So in this case, curl your fingers around counterclockwise as viewed from the top, and your thumb points up. If we reverse the direction of the current, then you got to curl your fingers clockwise, and your thumb will point down. And it naturally wants to line up with the magnetic field. That's what it wants to do. So when we talk about which way our loop's going to rotate, like this, they're going to rotate in a way that they're trying to line up with the magnetic field. Okay, so we can run current through a loop, like a coil. And in doing so, we can create a torque, a motor. Now we're going to amplify this effect by creating a coil, not just a single loop, but like N loops or N turns. What is that going to look like? Let's see, it's going to look something like this. Instead of just one single coil, I see that I've got 3 coils. Instead of just one single loop, I see that I have 2 loops. Okay, that N refers to how many loops you have. How many loops you have. Okay, so we can amplify this torque by creating lots of little loops. So we're going to use torque as mu cross B. Remember that mu points perpendicular to the page. But we're going to add this extra N that tells us the number of coils. And the loop is going to rotate so that mu aligns with B. That's what it wants to do. That's its moment, its inertia. But this time it's a magnetic moment. Okay, so let's look at these pictures first. Okay, we have a coil of N loops. In this case, it's like 3. And because this coil is flat on the ground, okay, let's see how that works. It's flat on the ground, and if I look at the current, it seems to be going clockwise as viewed from the top. So I'm going to curl my fingers clockwise, and that magnetic moment points straight up. If the current were flowing the other way, the magnetic moment would point straight down. But if I follow around that picture, the magnetic moment points straight up. Check. And same with this loop. Sure, it's a triangle, but it's still a loop, and the current still flows around, and the magnetic moment points straight up. Check. Now it's placed in a B field, that isn't quite straight up. It's offset. Yeah, here's straight up, and here's the B field, and it's offset. This wants to rotate. We run current through this loop. We can create a torque if everything is lined up, and it's going to do so that mu lines up with B. So this whole thing is going to tilt so that mu lines up with B. Okay? That's the direction of it. It's going to line up with B. So there's my B field. Okay, so my mu is pointing up this way. It doesn't want to point that way. It wants to line up with the B field. Okay? All right. So let's work this example. And then we've got a group work. And then we are done for the day. All right. So first, we have a rectangular coil. So we're looking at this first picture, our rectangular coil, and we're given the sides 2 meters by 3 meters. And we're told that it has 3 loops. And it's placed in a B field that has a certain magnitude, but notice how they're offset by 30 degrees. The current in the loop is 2 amps. We want to find mu of the coil and just the magnitude of the torque. Now we know that it's going to spin. It's going to, this side is going to physically lift up so that it lines up with the magnetic field. Okay. All right, let's get a whiteboard up. All right, so let's look first at part A. Part A, we have an area that's going to be 2 meters by 3 meters, so a 6 meter squared area. We have a B field that is magnitude 0.5 Teslas. We're going to run a current of 2 amps through that loop, and this loop has 3 turns or 3 coils. And the angle between these two is 30 degrees. That's shown in the picture, such that mu points straight up and the B field points this way, and the angle between them is 30 degrees. All right, so let's find the magnitude of the torque. Well, the torque is mu crossed into B. So the magnitude of the torque is mu B sine theta, where theta is between those two things. So this is going to be mu times B times the sine of 30 degrees. That's the angle between those two vectors. Okay, so what is mu? Well, mu is given by number of turns times the current times the area. So that's 3 times 2 amps times 6 meters squared. That is 36 amp meters squared. And the B field was given, oh, I don't need to write that down, it's just given, right? It's 0.5 Teslas. So the magnitude of the torque is mu, which is 36 amp meters squared, times the B field, which is 0.5 Teslas, times the sine of 30 degrees, and that gives us a torque of 9, and the units on torques are Newton meters squared, and I'm doing absolute values. Okay, so the magnitude of the torque is 9 Newton meters squared. And you can check the answer on the slide. Okay, let's go back and see that. There's our 9 meters squared. right there. Okay, cool. Now let's look at part B, and part B deals with the second picture. Same current, so we still have the 2 amps, but now our coil has a base of 2 meters and a height of 3 meters, and it only has 2 loops. It's in the same magnetic field that makes the same 30 degrees. And in case you forgot the area of a triangle, I'm reminding you it's 1/2 the base times the height. Okay. And we're going to get an answer that's going to be different. Why? Because the area of the loop is different and the number of coils is different. So same magnetic field, same current, same kind of 2 meters and 3 meters, but the second one will have a smaller torque. So if I want to create a motor with a lot of torque, I can increase the area or I can increase the number of turns. This one has 3 and this one only has 2. Okay, so let's do that. Whoops. Get a whiteboard. Okay, so now for part B, our area is 1/2 the base times the height. That's 1/2 the 2 meters times the 3 meters. And the area is significantly smaller. It's 3 meters squared rather than the 6 meters squared for part A. Also, we only have 2 loops rather than 3, but we have the same exact B field. We have the same current, and we still have the same 30-degree offset between mu and B, and that's all in the picture. Okay. So mu is NIA, so that's 2 times 2 amps times 3 meters squared, and mu is 12 amp meters squared. And so then my torque, the magnitude of the torque, is still mu B sine, that hasn't changed, it's still sine of 30 degrees. So this is 12 amp meters squared times 0.5 Teslas times the sine of 30 degrees, and this gives a torque of 3 Newton meters. Okay, so different torque based on different areas of the loop. Now, I think this is one of the cooler things that happens in electricity and magnetism is all this rotation and motors and engines and generators, which we're getting into. Okay, so it's literally as simple as run some current through a loop, place that loop in a magnetic field, and boom, you get torque. And that rotation can then do work. That rotation can do work. And if that rotation comes from electricity, it's called a motor. If that rotation comes from combustion, it's called an engine. Okay, last one. And at this point, I do urge you to kind of pause and try to set this up on your own. Set this up on your own, and then when you're ready, unpause and I can work through it. But don't just wait for me to work through it. Really try your hardest to set this up. And you might not get all the way, that's fine. But at least get to the point where you're trying to set this up. Notice the direction of the current. So this loop is flat on your desk, just like it has been before. But notice the direction of the current because you're going to need that to find the magnetic moment, mu. Okay. So actually, before we do that, well, no, yeah, just stop, pause, think about what I'm trying to say about the magnetic moment, set it up as far as you can, and when you're ready, unpause. Okay, so this loop is flat on the piece of paper on your table like this, okay? But now the current is flowing it's flowing clockwise as viewed from above, right? So if I take my fingers and I follow it around this way, oh, that magnetic moment points down. The magnetic moment is pointing down this way. So if I want the angle between the B field and the magnetic moment, well, I've got to go first the 90 degrees to get me to the y-axis, and then the 40 degrees above that, right? So that doesn't look good. Let me try that again. Okay, let me try that again. Here is our magnetic moment. It points straight down, right? That's a 90 degrees. It goes from the negative z to the y. From the negative z to the y, that's going to be 90 degrees. And then from the y, another 40 degrees. So that's 130 degrees. It is not the same as 90 minus 40. This is 90 plus 40. Okay. So I'm going to try and redraw that on a whiteboard. But that's the first thing you should do is say, oh, the current is flowing around this way, so the magnetic moment points straight down, straight down. And then let's see what other information we are given about this. We are given something about the area of the loop, so 2 meters by 3 meters. We're given the current. We're given the B field. It's a single loop, so N equals 1. And we want to find the magnitude and direction of the magnetic moment. Now we've already found the direction. It's in that negative z-axis, right? Points straight down into your page, down towards the ground in that negative z-axis. But we also want to find the magnitude of it. And then we want to find the magnitude of the torque. Okay, so let's try my best to redraw this and get those angles all taken care of. So I'm going to try and draw this like, let's see. The magnetic field is at 40 degrees, okay, that way, from like in the positive z-axis, above the z-axis. And the mu is down this way, right? So the angle between them is 90 degrees plus 40 degrees. That's the 130 degrees. Okay. So the loop itself is kind of flat right here. The loop itself is kind of flat right here. Right? So the magnetic moment, it's either going to point straight up or straight down. Those are our two options because the loop is flat. But the B field is offset. Okay. All right. So let's get this color. We want to find the magnitude of mu. Well, that is N times I times A. N is 1. The current was given to us as 5 amps, and the area of the loop was 2 meters by 3 meters. So I can write it over here. The area is going to be 6 meters squared. So the magnitude of the magnetic moment comes out to be 30 amp meters squared. And the direction is in the negative z direction. And that just came from curling my fingers around with the current. Okay, now let's find the torque. So the magnitude of the torque is going to be mu times B times the sine of the angle between them, which we have decided is 130 degrees. So the magnitude of the torque is, and we already found mu was our 30 amp meters squared. The B field given as 2.5 Teslas and sine of 130 degrees. And this gives a magnitude of the torque of 57.5 Newton meters. Okay. Now, the last question, that's a little bit tricky. It says, which way is it going to rotate? Well, without exactly knowing where the pivot point is for this loop, it's really hard to know. Is it pivoted around which axes? Oh, here it is. It's hinged along the x-axis. It's hinged along the x-axis, so it's pinned down here. It's pinned there, okay? And our mu is this way. It doesn't want to be that way. Which way does mu want to be? Mu wants to align with the B field. Mu wants to be right there, okay? So what's it going to do? It's going to flip upward so that it aligns with B. It's going to rotate upward. Let's see that. Let's try and see that, right? So here's your loop, okay? Now set yourself like an x-axis that you're going to hold your paper, your loop, your notebook. And mu is pointing straight down, but it doesn't want to be straight down. It wants to line up. So what it's going to do is it's going to flip up so that the mu aligns. However long it takes, it's going to flip up so that it aligns with it. Okay? So it's going to basically rotate by 90 degrees so that it aligns with it. Okay? 130 degrees, so that aligns up with it. That's just kind of a conceptual question. I'm not asking you for a number. But mu wants to line up with B, and it's pinched around the x-axis. So it could go all the way around this way, or it could go around this way, and that we would need more information to know exactly how it's going to rotate. But generally, it's going to take the least path, the path of the shortest distance, because that's the way physics works. Nature is lazy. It always wants to do the least amount of work. So when you're feeling lazy this semester, you can console yourself in knowing that the entire universe is lazy and operates on the idea of doing the least amount of work possible. Okay, so just something like the loop will rotate so that mu aligns with B. I mean, that's the whole point, is that mu is going to align with B. I think that's the end of our slides for the day. It is. But notice how we're getting into this really cool idea of making things rotate. How easy is it to use electricity and magnetism to rotate? Why electricity and magnetism? Well, because I have to have the magnetism from the B field. But the electricity is what's creating a current, right? So I have a loop of wire, nothing is going to happen. I run current through it, nothing's going to happen. But suddenly I place it in a B field, and if I line it up right, I get rotation. So now maybe this loop isn't just a loop, it is maybe a windmill, right? And now maybe this is a paddle that as it moves, it does some work. I've just created a motor that is capable of doing work. So run some current through a loop, place it in a B field, you get rotation. You can then use that rotation, as engineers do, use that to make it do something. Make it spin something, make it turn something, make it move something, make the wheels of a Tesla go. Okay? So we're getting into some cooler applications of electricity and magnetism. And then I just want to be very careful here to differentiate between a straight wire where we don't need to do an integration because the angle of that cross product doesn't change, and a curved wire where we do have to do that angle of integration because the angle is changing at every point. Okay. So our next topic is sources of magnetic fields, and we're going to be focusing on something called the Biot-Savart method. It's actually what I have on that whiteboard on my profile page, or on my profile picture. the whiteboard with the crazy vector calculus, that's what we're doing next. Biot-Savart is rough. It's made grown men cry more than once. It's made grown women cry more than once. It's not easy, but it is necessary to understand Biot-Savart. And what we're going to look at in the next topic is, but where does that magnetic field come from? So right now we're saying, hey, we have, magnetic forces and magnetic fields and currents, but we haven't really asked the question, but where do they come from? What is a magnetic field? Where is it coming from? That's the next topic. Topic 8, sources of the magnetic field. So feel free to stop into my office hours. I know this right-hand rule stuff it can be a little bit complicated, especially when, I tried not to mirror my image so that right is right and left is left. But it's really hard seeing it on a screen. So feel free to join my office hours. You know the drill. Send me a text, send me a WhatsApp, send me an email. And I hope you all have a wonderful day.